Hello and welcome back. In this video, we are going to look at some of the transfer functions that we are going to see in this series. The very first one is called hard limit, and in this particular transfer function, a is equal to 0 when n is less than 0, and a is equal to 1 when n is greater than or equal to 0. And the way we can visualize that is as follows. Let's say we have this x-axis, which is the value for n, and then we have the y-axis, which is right here, which is the value for a. And this axis we have 0, which is right here, and let's say this is 1. Now if we try and draw the values for a, what this tells us is if a is less than 0, so if a is anywhere here, the values are going to be 0. But if a is if n is less than 0, then the values are going to be 0 for a. But if the value for n is 0 or more, then we see this jump to 1, and then these values would be 1 all the way around. The next transfer function is symmetrical hard limit. So same hard limit but symmetrical. So symmetrical hard limit. Now with the symmetrical hard limit, the thing that changes is what happens when the n is less than 0. So if n is less than 0, we see that the value of a can go to -1. So it will be, instead of 0 limiting to 0, it will be -1. And if n is greater than or equal to 0, the value would be +1. So if this is like this, so the difference is just this value for 0. Here it becomes 0, here it becomes -1. And so when we try and draw this, let's use a straight line if I can. So if we have a line like this, and when we have a line like this, now if I try, this is what is our n, this is the value for a, and let's say this is the +1 for a, and then 2 down, let's say this is the -1 for a. Now when we try and plot the curve, what this above is telling us is that if the values of n are below 0, so if anywhere there, these would be -1, but as soon as n reaches 1, n is reaches 0 or above, then the values steadily become uh, +1. So that's how the transfer function would look like. And you probably already started saying what these type of transfer function help us do is convert any value into 0 or 1, or convert any value to -1 or 1. So if you are trying to classify something, these would be positive, negative classes that we are trying to create. The next transfer function is linear, and linear, as the name suggests, is pretty straightforward. A is equal to n. So what this tells us that let's say we have n, and we then have some value for a, then whatever value we have for n would be also the value for a. And in this case, this is shown here by this line, so that's the origin, which is at, so that's the 0. Next transfer function is saturating linear. So let's try to write that here, saturating linear. And in this case, rather than um, having a is equal to n for any range of values of n, here we put sort of a limit to that. So if n is less than 0, we say that a can be sort of capped at 0, and if n is anywhere between 0 and 1, including 0 and 1, then a is equal to n. So that holds there. And then if n is greater than 1, again then we cap that value of a to 1. Again, if we try and draw that, let's say this is the axis we have for a and n. So I'm going to label this is the n, this is the a we have, and let's say that this is where we have the plus 1, this is where we have the minus 1, and that's where we have the origin, which is 0. So what this is telling us is, if we have the values, if we have the values of a, values of n less than 0, so anywhere here, then a is going to stay 0 like this. But if the values are greater than 0, greater than equal to 0, but still less than 1, then we see something like this. Again, as soon as the values of n are greater than 1, then we see that this will again cap sort of saturate at 1. So we need to label the x-axis here. So if this is 0, let's say that this right here is 1. So let me write that down. So let's say that is 1 for n. So this range, so this is the sort of the range where we still see that diagonal line going through. So that's the range. Anywhere outside that range, the values are either 0 or 1. The next transfer function we are looking at is called symmetric saturating linear. So this is called symmetric saturating linear, and in MATLAB the short forms for these are, this is called Hardlim, and this is called Hardlim with an S. Then this is called Purelin, and this is called Satlin. Likewise, the symmetric saturating linear is called Satlin S. And in here, if the value of n is less than 1, then the value of a is -1. So we are going below 0 now. If the value of n is anywhere between -1 and +1, that is including -1 and +1, then we see that diagonal behavior. So a is equal to n, and if the value of n is greater than 1, again the value of a is capped at +1. So if we try and draw this, let's say that's our y-axis, this is our x-axis, and here we have the value for n, this is the values for a, and let's say this is +1, and here we have -1. Again, let's say this is the +1 for n, and let's say this is the -1 for n. Then the way we would try to draw this is as follows. We look at the values less than 1, less than -1, and that's where a would be -1. So this part would be -1 for a when n is less than -1, and likewise if n is greater than 1, then a is equal to +1. So that, and then this part is simply connects those two, such that if n is between -1 and +1, then we see that diagonal line. The next transfer function we are going to look at is log-sigmoid, and this is by far one of the most common. So log-sigmoid, and this is called as log-sig. Log-sig. With the log-sigmoid, the way we calculate A is as follows: A is equal to 1 divided by 1 plus e to the power minus n, and here, as you may know, n is equal to the values for w dotted with p plus b. So that's so essentially we are saying that this is going to be 1 plus e raised to power minus wp plus b. That's what this uh, transfer function would use to calculate, and the output of this transfer function is as follows. So we first draw the value, the y-axis, then we are drawing the x-axis, and then so that's our n, this is our a, and let's say this is plus 1, we have the minus 1. So the values for the log-sig, they stay above 0, and let's say this is 0.5. If the values are below 0 for n, then they start approaching 0, but they do not touch the uh, x-axis. So they do not drop to 0 for a, but they stay close to 0. And likewise, if they so I'm not able to draw this. Let's just draw a very small curve here. This is like a S-shaped curve, like this. So this value, it comes pretty close to plus 1 when the values are uh, above 0, and the values below 0, this would come pretty close to 0, but it won't touch the axis there. So that's the log-sig function, where the values stay between 0 and 1. Likewise with the Tansig function, so let's write that down. Tansig, or the full name would be hyperbolic tangent sigmoid. So with the Tansig function, the a is calculated as follows. We have e raised to power n minus e raised to power n minus n, and then in the denominator we have plus e raised to power n plus e raised to power minus n. And again, if we try and plot it, let's say this is our y-axis, and drop to here, then we have this is our x-axis, and let's label it. This is n, this is the a, and now if we try to get the plus 1 here, this is the minus 1. In this case, the similar concept as we saw in the log-sig would be there, except that the values this time would be between -1 and +1. So I'll try to draw this. So we would have something S-shaped curve that goes something like this. Again, the values will never touch -1 or +1. They'll be pretty close to +1 and -1, so something like that, and pretty close to -1, something like this. And this is the Tansig or hyperbolic tangent sigmoid transfer function or activation function. The next one is positive linear. So positive linear. and this is also called as poslin, and these are all MATLAB transfer functions. In this case, if n is less than 0, then a is equal to 0. If n is greater than, so let's let me write that here, n is greater than or equal to 0, then we have a is equal to n. So looks like if the values of n are greater than 0, then it behaves like a Purelin function. Let's draw that here. That let's get the straight line, and that's what we have for y-axis. Then this is our x-axis, and let's label this as n, label this as a, and as the values above suggest, if we have values of n less than 0, a is going to be 0, so it would be something like this. And then when the values of n are greater than or equal to 0, then we would see the values of a increase that way. So these are the transfer functions that you will see in this series on neural network design, and uh, these are the functions that you see. They may be shown in the neural network in form of a box. For example, you might see a box such as this one. You might see a box like this, and in the box you might see uh, the curve drawn symbolically. For example, something like this. You have a straight line, and then another straight line right here, then it goes up here, and then it goes like this. So what this box is telling us is that the transfer function we are looking at is the Hardlim transfer function, which is this. So this is the 0, that's the +1, and then this is the n, which is the x-axis, and that's the a, which is the y-axis. So these are the a, which is the y-axis. I hope in this video you got some intuition about the several common transfer functions that are used in neural networks, and there are several more, but related to this series, these are the uh, ones that we are going to see. If you have any questions, comments, or suggestions, please do let me know in the comment section below. I hope to see you all in the next video. Thank you.